Hello everyone, myself Dr. Dipika Narula. Currently I am working as an assistant professor of chemistry in the School of Basic and Applied Sciences, Maharaja Agrasen University, Baddi. So the topic which I have chosen for discussion today is aromatic electrophilic substitution. So let us first know what aromatic compounds are. Any compound which has a benzene ring system in it is normally called an aromatic compound, and we know that the benzene ring type systems, they follow the Huckel's rule of aromaticity, that is they have 4n plus 2 pi electrons in their system. So let me show you a benzene ring. This is the way how a benzene ring system looks like, and all systems which are identical to this benzene or which have a benzene ring in them, they are aromatic, right? So benzene ring is aromatic in nature. After this we have the next word over here, electrophilic. Electrophile is an electron loving species, means it is in love for electrons or negative charge. So itself it has a positive charge on it. So species of the type E positive, E over here I am referring to the electrophile. So E with a positive charge on it is an electrophile. So let me give you the basic representation of an electrophile. This is the way how we normally symbolize an electrophile. So here I am writing along with some common electrophiles, like this is nitronium ion. Over here we have the alkyl ion. Okay, so these are the common electrophiles. So electrophiles, they are electron deficient, that is why they are electron loving. And the last word which you can see on this slide, this is substitution. So substitution, it refers to replacement of one entity with another. So if I talk about now these three words together, which is aromatic electrophilic substitution, it means that we need to substitute a hydrogen atom, let us say on a benzene ring, with some electrophile, right? So let us continue further. So the next question which comes to our mind is, why particularly the aromatic compounds are chosen for aromatic electrophilic substitution reactions. So in order to understand this point, let us first consider what is the structure of a benzene ring. So these are, here you can see, these are the 6 carbon atoms in the cyclic ring system, right? Each carbon atom over here, we know that it is sp2 hybridized, right? So each carbon atom in benzene is sp2 hybridized, and after forming those sp2 hybridized orbitals, each carbon atom is left with an unhybridized p orbital on it. So now what I am going to do is, on each of these carbon atoms I am going to show you an unhybridized p orbital. So this is the way how the p orbital is going to look like, right? And each of these p orbitals, they have an unpaired electron in them, right? So now we can see that we have a plane of 6 carbon atoms, and each of those carbon atoms has a p orbital, and each of that p orbital has 1 electron each. So now these unhybridized p orbitals, they are going to overlap with each other, and we are going to get a rich pi electron cloud above and below the plane of this 6-membered ring, right? So this is the reason why electrophiles, they they attack the aromatic system, because the aromatic ring systems are electron rich because of the presence of a rich pi electron cloud. Okay. So if we have the clarity of these concepts now, let me give you the basic representation of an aromatic electrophilic substitution reaction. Right? So this is a benzene ring system, right? And let us say to this, if I add an electrophile E positive, so what is going to happen? This is the basic reaction. So here you can see that we have started with the benzene ring. To that we have made an electrophilic attack. So what is going to happen? Substitution is going to take place. One of the hydrogen atoms of the benzene ring system that is going to be replaced with an electrophile. So this is the aromatic electrophilic substitution reaction. Okay. Okay. So now let us discuss next that what is the mechanism of this aromatic electrophilic substitution. So we normally think that whenever we talk about mechanism, we try to understand the detailed mechanistic steps in which the reaction might have taken place. So here, when the researchers were working on this concept, they formulated that the aromatic electrophilic substitution is a two-step reaction. So the first step, it involves the attack of electrophile onto the pi electrons of the benzene ring. So let me show this to you diagrammatically with the help of the basic equation, right? So in the first step, what is going to happen? These pi electrons are going to attack onto the electrophile and we are going to get an intermediate rhenium ion, right? Let us say the electrophile attaches itself here. There was originally a hydrogen atom here and a positively charged. This kind of intermediate will be formed, right? In which now we can see that the aromaticity of the benzene ring has been lost and this intermediate has a positive charge on it. So that is why it is normally called cyclohexadienyl cation, or it is called a sigma complex because a sigma bond has formed between the carbon or electrophile, and otherwise it is also called a valent intermediate. And one very important thing of this intermediate is that can be stabilized. How? These pi electrons of the benzene ring, they can cause stabilization of this positive charge. So in continuation to this structure, we can draw more resonating structures also where this positive charge can get stabilized by the pi electrons of the system. So the first step is the attack of the electrophile onto the pi electrons of the benzene ring. And then in the second step, what is going to happen? The leaving group is going to depart. So the leaving group here is hydrogen. So hydrogen atom is going to depart in the next step. So if we have to understand how this is happening, this is the system, right? This is the way I am going to represent this sigma complex. So whatever base will be there in this system, that is going to abstract this hydrogen, and we are going to get the product where electrophile has taken the position of hydrogen, right? So this is the mechanism of aromatic electrophilic substitution, and whenever a mechanism is proposed for any reaction, some evidences are given with support that yes, this is actually the mechanism which is happening, right? So here also the scientists, they gave two evidences in support of this mechanism. So let us discuss these evidences one by one. Okay, before going into that, let me just show you the energy profile diagram of aromatic electrophilic substitution. So in the energy profile diagram, we know that it is a plot of energy versus the reaction coordinate, right? So here we can see that here we have mentioned the reactants, which is benzene ring and the electrophile. Then the reaction is going to pass through a transition state, right? In the first transition state, which is mentioned as TS1 here, we can very clearly see that electrophile has got bonded to the carbon atom, but it is not a very strong bond, right? So the bond between carbon and electrophile is long. And then this transition state 1, it is further going to change into the carbocation intermediate or the valent intermediate, which we just discussed. Then this intermediate is again going to transform into the transition state 2. In the transition state 2, we can see that the bond of carbon and electrophile, it has formed completely, but the bond of carbon and hydrogen, that is weakening, right? So that we have shown with a lengthened CH bond. And ultimately, then this transition state is going to give us the final product, which is the electrophile substituted benzene ring. So this is the energy profile diagram of aromatic electrophilic substitution. Okay, now let us come to the part which I was just discussing, which is the evidences in support of the mechanism. So the first evidence in support of this mechanism was the isolation of the rhenium ion intermediate. So what was done? The scientists, they chose mesitylene as the compound. This is the structure of mesitylene. Basically it is 1,3,5 trimethyl benzene is called mesitylene. They treated this compound with BF3, that's the Lewis acid, in the presence of ethyl fluoride. The temperature of the reaction was at minus 80 degrees Celsius. So when they subjected mesitylene to this reaction conditions, they were actually able to isolate the sigma complex or the valent intermediate which was expected to be formed in this reaction. So here, if we talk about the structure of the intermediate, this is how it looks like, right? Over here we have methyl, here also methyl, and here also methyl, and then we have H and an ethyl group substituted. So this intermediate, basically if I call it intermediate number 1, this was actually isolated from the reaction mixture, and then once after its isolation, when it was subjected to identical reaction conditions of aromatic electrophilic substitution, the researchers, they indeed got the final product in which here you can see that in which the electrophile was actually substituted at the ortho position of these methyl groups, right? So the isolation of this intermediate was actually an evidence of this mechanism. Another evidence for the rhenium ion mechanism, it was the isotope effect. So what was done? Initially benzene was chosen, an electrophile was added. So the reaction which was chosen, it was basically nitration reaction in which the electrophile which is added is nitronium ion, this NO2 positive. So what was done? One reaction was carried out in which benzene was reacted with this electrophile. In another case, deutero substituted benzene was used, and in the third case, trisio substituted benzene was used. So it was found that no isotope effect was observed. This means that there was no change in the rate of the reaction when either of the isotopically substituted benzenes were subjected to this nitration, which is an aromatic electrophilic substitution reaction. And this subjected that the bond of carbon hydrogen or the bond of carbon deuterium or carbon tritium, that is not broken in the rate determining step of the reaction, which we initially proposed. So we know that the rate determining step of the reaction is the attack of the electrophile onto the pi electrons of the benzene ring, right? So the first step of the mechanism is the slow step, and this was confirmed by this evidence. Okay, after this, let us discuss some typical aromatic electrophilic substitution reactions. So one which I just discussed with you, that is the nitration. In order to carry out nitration in the laboratory, we normally choose a mixture of nitric acid and sulfuric acid, and one thing which we require, that is a benzene ring system. So this mixture of nitric acid and sulfuric acid, this is called a nitrating mixture. So upon nitration, the active electrophile which is generated by this combination, that is nitronium ion. So ultimately the product which we get here is this nitro substituted benzene. So this is the most common and most widely employed aromatic electrophilic substitution reaction. Coming to the next one, another aromatic electrophilic substitution reaction which is commonly encountered is sulfonation. So sulfonation, it normally refers to the introduction of a sulfonyl group, SO3H group, which is called a sulfonic acid group, to the benzene ring system. So in order to introduce an SO3H moiety, we need to treat benzene with sulfuric acid. Either we can use sulfuric acid or we can use oleum, right? So in order to represent it through a reaction, this is benzene. So if it is treated with sulfuric acid, which is H2SO4, so it leads to the formation of SO3H, sulfonic acid substituted benzene. So the active electrophile which is working here and which undergoes the attack, that is SO3. This sulfur trioxide molecule, this sulfur trioxide is the active electrophile which is going to attack on the benzene ring. And then in all these reactions now which we are going to discuss, in that all these are going to follow the same mechanism to substitute an electrophile, right? Okay. Then after this, the third most commonly encountered typical aromatic electrophilic substitution reaction is halogenation. So as is very much clear from this word halogenation, it means the introduction of a halogen substituent onto the benzene ring system. So very commonly the halogen or a halo moiety that can be introduced by treating the aromatic system with halogen like chlorine, bromine we can use in the presence of a Lewis acid catalyst. So the most common Lewis acids or which are employed is we can use zinc chloride, zinc bromide, aluminium chloride, aluminium bromide, all these can be used, right? So let us say this is the benzene ring system, we treat it with chlorine here and we can use AlCl3 here, right? So the electrophile which is going to be generated by this combination, that is Cl positive. This Cl positive is called the chloronium ion, right? And then we can get the product in which a halogen substituent has got substituted onto the benzene ring system. So three aromatic electrophilic substitution reactions we have just seen. One is nitration, second one is sulfonation, and third is nitration. After that, two most important electrophilic substitution reactions which have the common name of the scientist who discovered them, that is Friedels alkylation. So alkylation, we know it is the introduction of an alkyl substituent onto the benzene ring. So alkyl means any R substituent, right? So let us say this is the aromatic system. Treatment of this with an alkyl halide. R over here refers to the alkyl, X is the halogen. So treatment with an alkyl halide, particularly in the presence of any Lewis acid catalyst like AlCl3 will work here. AlCl3, AlF3, AlBr3, all these will work. And ultimately, the product which we are going to get here is the alkyl substituted benzene ring, because this combination of alkyl halide and Lewis acid, that is going to generate the electrophile which is the R positive ion here. So you might have noticed that in all these reactions which we have seen, electrophile is normally carrying a positive charge on it, right? So this is the fourth one, and the fifth and the last one which is encountered, that is Friedels acylation. So first let us see what is an acyl group. C double bond OR. This kind of substituent is commonly referred to as an acyl substituent in chemistry. So Friedels acylation means the introduction of an acyl substituent onto the benzene ring. And very similar to the Friedels alkylation, it is done in a similar way. Here also we take the aromatic system, treat it with an acid chloride in the presence of a Lewis acid catalyst. So similarly, the acyl group will get substituted onto the benzene ring, right? So let me show you the reaction. Here we have taken the benzene ring system, then we have treated with an acyl halide in the presence of a Lewis acid catalyst like AlCl3, and we are going to get the C double bond OR. So you can see that an acyl substituent has got attached at this position, and the active electrophile in this case is this acylium ion, this which I am drawing below. This is the active electrophile in this case, right? Okay. So I have given you till now that what is aromatic electrophilic substitution, what is its mechanism, energy profile diagram, and 5 most commonly encountered aromatic electrophilic substitution reactions. Now I just want to tell you in brief about the activating and deactivating groups, right? Now we know that benzene ring is electron rich, right? If we take individually benzene, it is electron rich. Now let us say that I have a benzene ring system, but some substituent is present on the benzene ring, right? Like this is the benzene ring, and now any substituent X is present here. If the substituent X is of electron donating nature, it is going to donate the electron density to benzene ring. So benzene ring will be now more electron rich. So it will be more easier for the electrophile to attack on the benzene ring, and then consequently we can see that the substitution has taken place, right? The substitution will become easier. It will occur at a faster rate. So such kind of groups which when present on the benzene ring increase its reactivity towards aromatic electrophilic substitution, these are called activating groups. So if I have to name some activating groups to you, they are OH, OR, then we have NH2, NR2, right? All these kinds of substituents, they are going to increase the electron density on the benzene ring. So they are activating. And now let us discuss the second category of this, which is deactivating groups. So if any substituent if present on the benzene ring, if that substituent is going to make the ring deficient of electrons, like let us say I have nitrobenzene or cyanobenzene. So nitro, cyano, such groups are going to withdraw the electron density from the benzene ring. So now the benzene ring will be deficient in electrons, and now it will be much more difficult for the electrophile to attack onto the benzene ring system. So all the such systems, they all such groups are going to make the benzene ring more electron deficient, and they are going to deactivate the benzene ring towards aromatic electrophilic substitution reaction. So some deactivating groups I am going to tell here. Nitro is a deactivating group, cyano is a deactivating group, aldehyde, ketones, all these systems are deactivating because they are going to make the benzene ring electron deficient. Okay, one last category which is left here is the halogens. Normally we know that, let me show it here. Normally we know that if this is a benzene ring which has a halogen substituent on it, so we know that the halogens, they are going to give their lone pair of electrons to the benzene ring. So the halogen moiety is going to give plus R effect, but at the same time the halogen moiety also shows minus I effect because it has the tendency to withdraw the electrons from the benzene ring. And if I talk about this halobenzene, then the minus I effect is stronger than the plus R effect. So here, if the minus I effect is stronger than plus R, then overall this group is going to deactivate the benzene ring towards aromatic electrophilic substitution because it is going to withdraw the electrons from the benzene ring system, and ultimately the ring is going to be deficient and attack is going to be difficult, right? So this was the concept of activating and deactivating group. So with this I end my presentation. Thank you.